This is a PID overview demonstrating a working PID loop using a DL06 and DirectSoft. We're using the F0 2AD 2DA-2 voltage input and output analog module to send and receive signals from a custom PID application, and this is in slot 1 of the DL06 PLC. Next, we'll set up the PID loop. In DirectSoft, go to the PLC menu, Setup, and then PID, and you will see the window pop up, Setup PID. It has the number of loops you've configured, and the first tab on any particular loop is the Documentation tab. The Configure tab is the next tab. You specify, first of all, the algorithm, either position or velocity. 99% of our loops are position loops. If you don't know which one to pick position. Next is the sample rate. The default is the fastest rate at 50 milliseconds. You can make the rate higher but not lower. Next is the forward acting versus reverse acting loop. Forward acting, the best way to describe this is if the output goes from minimum to maximum, does the PV value go higher or lower? If it goes higher when the output goes higher, then that's a forward acting loop. Or if the output going higher causes the PV value to go lower, that's a reverse acting loop. Next is the transfer mode. Bumpless transfer 1 or bumpless transfer 2 are the selections. When the PID loop goes from manual to automatic, both modes copy the output value to the bias value so they're equal when the loop goes from manual to auto. Bumpless transfer 1 also makes the set point equal to the PV value at the moment of a manual to auto transition. So if you don't want the loop to change your set point value, pick bumpless 2. But bumpless 1 provides the smoothest transition because since the set point and PV are equal and the output and bias are equal, theoretically no control action should occur since everything is balanced. The next section is setting up for the input and output resolutions of the values. The SP, PV, and output format, if you pick common, means that the input and output resolutions are the same. If they are different, you would pick independent format. If you pick common format, then you set the information for both input and output on the same location, unipolar data or bipolar, and 12, 15, or 16-bit. Lastly, the loop mode independent of CPU mode. This is normally not used if you have a PID loop that must continue running even if the PLC goes out of run mode, even for a fault. Then you would check this mode and you would have to set up auto transfer for your output at least and probably your input so that the loop would continue running even though the PLC is not in the run mode. But be aware this is a potential safety hazard. On the SPPV tab, the address and or nickname is supplied for the set point variable and the process variable. If you're doing cascade loop, you would set up the remote set point for cascade loop output. If you want to do limiting of the set point value, you can check that here and enter the upper and lower limit values. Be aware that can be problematic because nothing tells you that the PID loop is limiting the value, even though you see that it can't go above or below some specific value. The process variable, you have the option of auto transferring. You can transfer from an I/O module directly or view memory. In most cases, a simple single rung ladder logic rung will take care of moving the PV value into the PV location, so it's really not needed. And there are code examples in the manual to cover the filtering if you want to filter the PV value without using the filter value here. There's also the option to square root the process variable. This allows for better error handling in some processes, but if you don't know that you need it, then just don't use it. In the output tab, you set up the minimum upper limit and lower limit based on the maximum range, which was defined by the bit resolution of the output. We set that up in the configure tab. Notice here we have a lower limit of 1433. This is because our PID process that we're using to demonstrate with, any value below 1433 on the output causes the fans to stop running, so we don't want to shut them down even at minimum, so we make sure that they never go below the minimum value. Then on the tuning tab, we have some values that we've come up with: the gain, which is proportional; reset, which is integral, which is in seconds or minute units. We have a freeze bias option, which is our anti-windup and should be used unless you know you don't need it. And then the rate is our derivative calculation. And there are some limits you can add to the rate itself. We also have some error calculations, including a deadband or squaring the error. Again, if you don't know that you need these, then don't use them to start with. There are also two additional tabs to the right of the tuning tab: the alarms and the ramp soak table. If you're not using alarms or ramp soak, then don't fill out those pages. Now I'll go over the ladder logic code. Rung 1 covers our standard disclaimer. Rung 2 sets up the analog card F0 to AD to DA-2. We start with the first scan bit. We go to load 2 input and 2 output BCD channels. The analog input register starts at V2000. The analog output register starts at V2002. The next three rungs, 3, 4, and 5, determine whether you use a first order filter with the PV value or not. Rung 3 checks to make sure the PV filter value is not 0. If it is, it makes it 1.0. Rung number 4, if C1000 is off, we do not want to use the first order filter. In that case, we load the first analog input channel at V2000. We convert it to a binary value and then output it into V4003, the PID PV location. If C1000 is on, we want to use the first order filter. This filter is shown in the analog module manual. We load the analog value, convert it to binary, then to real. We subtract the previously saved value. We multiply the difference by our filter value. We add that back to the previous value, and then we output it for the next iteration in V1400. Turn that real number back into binary, and then output it to the PID PV location at 4003. Rung number 6 loads the PID output value and moves it to the analog output value with an SP1 always on contact. It loads V4005, converts the binary to a BCD value, and outputs that to V2002. Rungs 7, 8, and 9 allow the change of the PID mode between automatic and manual using the C0 bit. If C0 goes from off to on, or if the first scan bit fires, that requests automatic mode on the PID by setting V4000.1. Since the first scan bit can trigger a request to go to automatic mode, we also make sure on a first scan that we set C0 so that the bit state follows the PID state at the start of the ladder logic scan. And rung 9 does the opposite. If C0 goes from on to off, that sets B4000.0, which requests manual mode. Rung number 10 sets up the PID table so that if you trigger an auto-tune straight from the auto-tune enable bit, it is already set up for closed loop tuning and PID tuning. The last four rungs, 11, 12, 13, and 14, make a very basic high-low PV value capture that's stored in the PLC. Rung 11 is the reset using a C2 bit to load a very high value in the low register and a low value 0 in the high register, and then resetting C2. This also happens on a first scan bit. Rung number 12 captures the highest PV value since the last reset. If the current PV value is higher than the stored highest value, then we load the current PV value and put it in the PV highest value. Rung 13 does the same thing for the low PV value. If the current PV value is below the lowest stored value, we load the current PV value and output it to the lowest PV value. And rung 14 calculates the difference. As long as the highest value is equal to or greater than the lowest value, we load the highest value, subtract the lowest value, and output the difference into the PV band. Now that we've covered the ladder logic code, we'll look at a data view window which holds the important controls in this program. You could use a CMOR to do the very same thing, but the data view allows us to do pretty close to the same monitoring and control. The first value is V2000, which is the analog input raw value. We're actually getting this from a fan which provides a 0 to 10 volt output based on the speed, and it's being controlled by two other fans that we're driving with the next value, which is V2002. And this output drives the two fans, they blow the other fan, it spins, and we get a closed loop PID that way. Both values are quite noisy because that's the raw value with no filtering involved coming straight from and to the analog card. V1402 is the filter value for our first order filter. Right now we're using a 0.5, which is half of the possible range, 0 to 1.0. 0 would not allow the PV value to change at all. 1.0 would not do any filtering, so effective values would be higher than 0 and below 1.0. C1000 is how we turn the filter on and off. If the C1000 is on, we want to use the first order filter. If we turn it off, then we just move the raw PV value from the analog card straight into the PID PV location. V4002, 4003, and 4005 are straight from the PID loop. 4002 is the set point value. You see it's not changing. 4003 is the PV value, whether that's being moved directly from the analog card if we're not using the filter, or from the first order filter output if we decide to use that filter. And the last value is the output going to the analog output channel from the PID loop. C0 is how we control the PID loop from manual and auto. If C0 goes from off to on, we go from manual to auto mode in the PID, and if C0 goes from on to off, we go from auto to manual in the PID. The last four values are the basic high-low capture in the ladder logic code. V3000 is the lowest value since the reset was triggered for the high-low capture. V3001 is the highest value since the reset was triggered, and V3002 is the difference between the high and low. And the ladder logic is set up so that if we turn on C2, it resets the high and low values and then turns off C2, so it's ready to go immediately. Now we'll look at the PID loop itself. If you go to View, PID View while you're connected to the PLC, we'll see the PID View window with its own tab. Beside that is the ladder view if you want to go back and look at the ladder logic, but we're going to stay with the PID view for now. First thing we want to do is change the size of the graph. You grab the bar below it and just drag it to the position you want. If that's not enough, you just move it further down or up. Now we're looking at the graph of the PV and the set point value on the top part of the graph, and we're changing the seconds per division to be 5, so we get the quickest graph with the most detail possible. We also look at the setup, and for now we don't have the manual scaling set, so it is auto scaling based on the current high and low values. You see 2010 at the bottom of this scale, 2080 above it, and 2045 is about the center. And the values below, we can see and change all the values associated with the PID loop. To change a value, you would highlight it, put the new value in, and hit the enter key to accept that value. If we were doing auto tuning, we would auto tune using the bottom part of that section. And then on the left hand side is a faceplate representation for each PID loop. It has meters for the PV and the output. If you double click on it, you have the option of going to the program mode, so you can go directly to the PID setup, but we're going to cancel that for now. Let's set the PID view graph from auto range to manual scaling, and we'll set it to 0 minimum, 4095 maximum for the full scale of the PV value. Now we're seeing the PV value in the middle of the scale at 2047 set point. The bottom of the top graph is 0 and the top of the top graph is 4095. Now let's change the set point to 3048, and we should see, as soon as we accept the PLC change, the dark blue line of the set point increases and the PV line increases to get to the set point. You see a little bit of overshoot, and then it should fall right in line with the set point value on the line. Then we'll go back and set the set point back to 2048. As soon as we hit enter now, the dark blue line goes back to the 2048 value and the PV starts following that. You see a little more undershoot than you did overshoot, and then it comes back and starts settling on the set point value. This looks like a nice smooth line and a smooth graph because we're looking at the full scale of the possible value. If I go back to setup and set this back to auto scaling, it immediately changes the upper and lower limits to include just the values that are on the screen. So we get a little rougher looking PV value, but it's still the same PV. We're just looking at it at a different scale on the graph, and as soon as the graph has a lot smaller values to deal with, you see the PV value gets a lot noisier. Even so, we're holding a fairly stable PV value with very little over and under of the set point relative to full scale value. If we go back to 3048, we see the scale change immediately. We see the overshoot again, but it's more dramatic looking because we're seeing less of the scale. Go back and change the set point again to 2048. See the drop in PV, the more dramatic undershoot, and you see the scale changing on the graph, and then it comes back to the set point and settles down again. Now we're getting back into a bigger zoom because the range between the minimum and maximum on the screen is a lot less. And keep in mind, this is with the first order filter on. If we turn the first order filter off, so we're not doing any filtering, you immediately see the output value doubles in the amount of range, and the PV value pretty much doubles as well. That's with no filtering, just the raw analog value coming in. If we turn that first order filter back on, we immediately see this output settle down and the PV value is less noisy than it was before.